Okay, so now I'm going to show you a different example of a resistive force. This is a force you're a little more familiar with. Friction can be a resistive force. In fact, air resistance and friction are very much related to each other. So this is an example where you've got some block sliding along a plane and there is friction. So it starts out with some initial velocity to the right. We'll just call that v, or you could write it v naught. And you've got this resistive force of friction, which normally is mu times the normal force. However, in this particular problem, the problem will state that the friction force is equal to minus kV. So whenever you see it in that form, then you know that you're dealing with this type of resistive force problem. So again, we're going to start with the force diagram. Normal up and gravity down cancel out. Friction opposite to the direction of motion, which brings you right down to this net force equation. Since there's really only friction acting, you set that equal to ma, and here you go. Here's your acceleration. So there's a very quick outcome of this type of problem. But now let's say this problem asks you to find the velocity of this thing as a function of time. So it starts out moving with some initial speed, and it's just gradually going to slow down to a stop. But what does that velocity look like as a function of time? Okay, so the strategy is to start here, your acceleration, which can also be written as the derivative of the velocity with respect to time. So now all I'm doing is rewriting this equation, but replacing the a with its differential form. Now I have velocity and time in there, which is what you need if you're trying to find velocity as a function of time. Okay, so calc people, you might already recognize that we need to integrate here, but you can't integrate when you have different variables on the same side, so now you want to group the variables together. If you rearrange this, you get dv divided by v equals minus km dt. K is always going to be a constant, as is the mass, so you can just pull those out. Okay, so the form of the integral looks like this. You can do this as either an indefinite integral or as a definite integral. The first approach I'm going to show you is the definite approach. Okay, so you integrate from the initial velocity on the velocity side of the equation to velocity at some later time. This is what we're actually looking for here. On the right side of the equation, you're just integrating from 0 to some later time t. Okay. The antiderivative of dv over v is the natural log of v. Those of you who have not had a lot of calculus, we haven't covered this yet. We'll talk about this more in class, but this is just the antiderivative. Anytime you have the derivative of a variable divided by the variable itself, the antiderivative of that is always just the natural log of the variable itself, and then here's the limits of integration. Over here, the integral of dt is just t, okay? So when you plug in these limits, you end up with natural log of v minus natural log of v naught equals minus kt over m, because the 0 for the second term just cancels out the second term completely. One of the properties of natural log is that when you have the natural log of one variable minus the natural log of another, you can rewrite it like this: the natural log of the quotient of those two variables. There's a reason why I'm doing this, but this is a property of natural logs. Those of you who have seen this before, that should be familiar to you. So I'm just rewriting it from this line to this line. The way algebraically to cancel out a natural log is to take the exponential function of both sides. The exponential function is actually e to the power of, okay? So when you times both sides of this equation by the exponential function, this whole term becomes the exponent for the exponential function over here, and the natural log completely just drops off. So what we would have is v divided by v0 equals e to the minus kt divided by m. I just skipped one step and multiplied by v0 on both sides to move that over here. So what you end up with is v, that's this v right here, v as a function of time, is equal to v initial times e to the minus kt over m. So the general form of this equation makes a lot of sense with what's happening here, because at time t equals 0, e to the 0 is just 1. So you have initial velocity. And as time goes on, this function is going to get smaller and smaller and smaller and approach 0. That's exactly what happens with the velocity of a sliding object that's experiencing a resistive force under friction. So I'm going to stop right there. So there's your velocity as a function of time.